Suppose you have a data point with two classes, class A and class B, and you have to find some type of boundary, some type of decision boundary that will allow you to separate these two classes. Let's say this is that boundary. Support vector machine, it allows you to do that. It's a supervised machine learning algorithm. It can be used for both classification and for regression. For classification tasks, that is the most common use case of your support vector machine. Now, when it is used for classification, it is called SVC, Support Vector Classifier. SVM are used for both linear and nonlinear classification type of problems. Imagine you're separating spam versus not spam emails, cancer versus non cancer patients, loan approved or rejected cases. So let's say one of the class is class A and the other one is class B. Now, there are many decision boundaries you can draw. You can draw this line, you can draw this line, or you can draw this line right here. And each one of these lines, they separate your class A and class B. But which one is better? So your support vector machine, it chooses the line that is the farthest from both the classes. And this way it gives you a better generalization on the new data. So in the below case right here, you can see the line L1 is closer to class A right here. Line L2 on the other hand is kind of like halfway in between your class B and class A. This is my class A right here. And line L3, on the other hand, is more closer to your class B right here. So by looking at these three diagrams, you can tell that your line L2 would be a better option because line L2 is furthest from both class A and class B. So this is a good line to create a boundary between two classes. Now your line L2 is a halfway between the two class. So what it means is this: if I take line L2 and I move it in this direction, I'm going to hit one of these points on class A. And likewise, if I take line L2 and I go in this direction, I'm going to hit one of these points on class B. So this distance is going to be equal to this distance right here. And this distance, this right here, is called margin. So why does SVM, it chooses a line that is furthest from both classes? Well, that's because it wants to achieve a better generalization to new unseen data. Now let's understand this through an example. So suppose I have this line L3 that acts as a decision boundary between your class B and class A. And you can see that this line is very closer to your class B. Now, if I have this new unseen data right here, and just by looking at this, you can tell that this should have been towards class B. This actually belongs to class B. But according to this decision boundary, this is going to be classified to class A because it falls on this side. So that's why you want to make sure that you pick up a right line that best separates both the classes. Now I'm going to introduce you to few terms that is used in support vector machine. The line or the plane is referred to, is also called an hyperplane. That would be this right here. The closest data point to the hyperplane, these are called support vectors. That would be these points right here. This one, this one. Let's say these are the points that are very close to your hyperplane. So these are called support vectors. And the distance between the boundary and the support vector, they are called margin. So right here, this one, this distance, and this distance, they are referred to as margins. Now, in any hyperplane, it can be written through this expression right here. In this case, your W is a vector. It represents the direction of your hyperplane. So suppose this is my hyperplane right here, this one. And in this case, W would be a vector normal to the hyperplane. That's what your W refers to. B is a scalar value. It determines how far is your hyperplane is from the origin. If let's say this is my origin in a three-dimension case, so this is my x-axis, this is y-axis, and let's say this is your z-axis right here. So B would represent how far this hyperplane is from the origin. Now let's look at the equation of hyperplane in two dimensions. So suppose your x is any point on a hyperplane, and let's say your w is given by this vector and b equal to this. Then the equation of a hyperplane is given by this expression, putting the values in there, putting the values for w and x and b in there. This would be equation of the hyperplane. This is right here. I drew this hyperplane. So in this case, this is my x1 and this is my x2. And this is the line that represents this hyperplane. Let's take a look at an example in 3 dimension. So this is an any point on a hyperplane. Let's say my w equals to this, and let's say b equal to -3. By the way, b can be -3. Then the equation of the hyperplane, according to this equation, putting the value of w and x in there, you will get this expression. So this will be for the case of 3 dimension, and this is your hyperplane right here. So the goal of SVM is to find this maximum separating hyperplane between the different classes of points. At the same time, minimizing the classification error. Now, this maximum separation, it has a special name. It is called maximum margin. In other words, in order to find this maximum separating plane, you have to find W and B. And SVM, it finds your W and B from the training data. Now, SVM, it only uses points that are closest to the boundary. In other words, it uses support vector. And these points, they determine your W and B of your plane. So in this case, this is my support vector right here. And let's say this is my support vector, and this support vector, and this support vector. If I remove these support vectors, then my W is going to change and my B is going to change. And therefore, the boundary will also change. So in this case, let's say I remove this point. This is taken out and this is taken out. When I remove these points, I will get a boundary that will be like this right here. And you can see that this boundary is now changed because I removed the support vectors. On the other hand, if I remove any non-support vectors, then your W and B are going to remain the same because it does not affect your boundary. So let's say I remove this point, or maybe I remove this point. Well, your decision boundary is not going to get affected. Your SVM will still be able to find your right decision boundary because it's only using support vector, which are these vectors right here. Now, in support vector machine terminology, you're going to hear these words hard margin, soft margin. In hard margin, there will be no data point inside the margin. It tries to classify everything perfectly. In other words, it overfits. So in this particular instance, let's say this is my class A, and let's say this is my class B. So this would be my decision boundary right here. And here you can see nothing in between. There's no point in between that is misclassified. Everything is perfect. So in this particular instance, my hyperparameter C is going to be very large. On the other hand, in the soft margin, there can be few data points inside the margin. And you can see that in this particular instance right here, this data point is inside, this is inside, this is inside. So this is allowing you some violation. So this way, it gives you a better generalization. And this way, your model would be less overfitting. In this particular instance, your hyperparameter C is going to be small. This is more realistic for real world tasks, real world ML tasks. Now, hard margin, it is less robust to outliers. An outlier can ruin its boundary. So let's understand this through this example. In this instance, this is my actual boundary, and I introduce an outlier. And because of the introduction of this outlier, now your boundary is going to shift. So this is going to go in that direction because in hard margin, it does not allow any error. On the other hand, soft margin, it is more robust to outliers, and that because it allows some errors. So in this particular instance, let's say this is my outlier point and this is my original boundary, and because of the presence of the outliers and also because this is a soft margin, it is going to be more forgiving. It is going to allow this outlier to be present over here, and your boundary is not going to change. It is not going to shift. Now, scikit-learn from Python, it has a package, SVM, that allows you to find the hyperplane and also perform the classification. So suppose this is your data point right here. These are my 7 data points, and these are your points right here. This one and this one right here. So, and for each one of these points, these are the corresponding labels. The first 4 points are class 0. So this one is my class 0. So this right here is a class 0. And the next 3 points, they are class 1. This one right here, class 1. So in this case, you just specify, you just call your model. In this case, I'm specifying my kernel to be linear. I'm training the model, and then after that I'm testing it on one of the points. So let's say one of the point is 2 comma 2. Let's say this one right here. Now it classes that 2 comma 2. It makes a prediction that it is going to be class 0, which is perfect. It was class 0. On the other hand, this point 8 comma 4, that would be somewhere over here. So 8 comma 4 is going to make a prediction that it belongs to class 1, and this belongs to class 1. All right, perfect. Now, what if the points are not linearly separable? So, for example, in a one-dimensional case, these points are not linearly separable. In the two-dimensional case, these points are not linearly separable. So, this point could represent, for example, drug dosage. So, red points right here, this one and this one, they would represent that the doses did not work, either because they were too low or because they were too high. So these are your red ones. And the green ones, they represent the dosage that works. So these are just the right value, just the right amount. And in both cases, I cannot draw a line. I cannot draw like a point, like a line over here that will separate green from the red, or maybe draw a line over here. This is not going to work. Same thing over here. I cannot draw a line where I can separate red points from the blue points. There is no way, because these points are not linearly separable. So in these types of situations, there are two solutions. The first one is soft margin, as I explained previously, where you allow for some errors, and the other one is kernel function. Another name for that is a kernel trick. And the idea is this, that you project your data points into a higher dimension. And this way your points get linearly separated. So let's take a look at the example of this one right here. So here I'm projecting my one dimensional point into two dimensional, and by projecting these points, this one gets projected over here, this one gets projected over here, these 4 points gets projected over here, and likewise these 3 points get projected over here. And now after I project my one dimensional point to two dimensional point, I can draw a line right here. This line will linearly separate these two classes. Let's take a look at the example of two-dimensional case right here. In this instance, I have this point in two dimension. They are not linearly separable, but by projecting these points in 3D, now you can see that you can separate these points by drawing a hyperplane at this place right here. Now, since you are going from a low dimension to a high dimension, you are creating a new variable, a new dimension. And this new dimension is created using a function called kernel. Let's understand this through an example. We're going to use kernel trick to go from one dimension to two dimensions. So suppose you have data points right here. These are your data points, x, right here. And these are in your one dimension. Now, clearly, you can see that this data point is not linearly separable. But suppose now we use this kernel function. And by using this kernel function, these points is going to get mapped to two dimensions. This is my one dimension points, and they get mapped to two dimension. So your -2 will get mapped to -2 comma 4. So -2 will be this point, and this is going to get mapped to this point right here. This point right here will get mapped to this one, and likewise this point will get mapped to this, and so on and so forth. And now we can see that these points are linearly separable in two dimension. I can draw a hyperplane like this, and this line will separate your red points from the blue points. Now let's take a look at an example of kernel trick by going from two dimension to three dimension. So these are my two dimensional points, and you can see that blue points cannot be separated by a hyperplane from the red points. So in this case, I'm using this kernel function. And by using this kernel function, each point will get mapped to a three-dimensional point. So this is my two-dimensional. This gets mapped to a three-dimensional point using this function right here. So in this case, -1 comma 0, that would be, let's see, x1 is -1, which is this point. This point will get mapped to -1, 0, 1. So this will get mapped to one of these points, and I believe that would be this point right here. So it's going to get mapped to this. And same thing with the rest of the point. They all going to get mapped over here. And now you can see that visually, you can see that you can have a hyperplane somewhere in the center right here. And this hyperplane will separate the red points from the blue points in a three dimension. In the two dimension, you were not able to do that. Now let's look at some of the advantages of SVM. Well, it works well. It works pretty well with the complex data. It can handle both your linear and non-linear data effectively. SVM, it can be effective in high dimensional spaces. So even when you have more features, in other words, more dimensions than the sample, this will still work. So that's what makes it useful when you're dealing with problems like text classification or image recognition. And it's also robust to outliers. We saw that through that example. Also, it avoids overfitting by using the margin, by using the hyperparameter C, it avoids overfitting. Also, it's very versatile with kernels. By using different kernel functions like linear, polynomial, radial, you have many kernel functions. By using these different types of kernel function, it can adapt to various types of data and solve complex problems. Another interesting thing you can do is you can combine kernels, and this way it gives you more complex hyperplanes. And of course, SVM also has some disadvantages. So it tends to be slow with a larger data set. It can be difficult to tune. Choosing the right kernels or parameters like your C and gamma can often be tricky, and often it requires a lot of trials and error. Also, it gives you poor performance when your number of features is more than the number of samples, and it can be hard to interpret. So, unlike some other algorithms, they are not SVM models are not easy to explain, especially when you're dealing with non-linear kernels. And also, it can be very tricky. It can be hard to find the right kernel.